Okay, so it's time for the second speaker of the afternoon. So I would like to welcome Espath, assistant professor at the University of Nottingham. He has been working with the group since 2015. And yeah, it's nice to have you back. And yeah, thank you for accepting the invitation.
Thank you for the invitation. Thank you, Raul and AJ. Today I'll be discussing basically three works we came up with Rojas, Krumscheid, Raul Tempone, and other collaborators that I don't mention here because I will be focusing on the last part of this work. But this is also a joint effort with Jonas Kisling, Dmitry Kabanov, and that's all. So in this work, the main idea is trying to combine the physics of fluids with statistical learning, and in a tool that we call Physics-informed Spectral Learning. And physics-informed comes from the physics of fluids. Of course, it can be something more general than fluids, but that's my interest. Then spectral makes reference to the fact that we have spectral convergence, and learning to statistical learning. The first part of this work appeared in Physics of Fluids when we deal just with divergence-free approximations, and the second part is under review on basically on the discrete Helmholtz decomposition. And what I am going to discuss later today is mixed problem and stability properties. Okay, so let me give you some ideas of the notation that we will be using here. We let psi here be a vector function from Rn to Rn, and this function, it's a real valued vector field in a domain D. This domain is a torus, and with the length di per direction. For the first problem I'm going to show, we are going to consider that we have a set of observed point-wise vector measurements of an unknown field measured at the locations xi, and we are considering that we have limited access to this field in p points. Then in the first problem, we will seek to perform a divergence-free projection of this unknown field. And in the second problem, we are going to decompose in a divergence-free field and a curve-free field components. Okay, so really important to what follows is to bear in mind this alpha hat. This is a multi-index where we have components here that are integers, and these are the dimension of the length of the domain per direction. So this will be a real multi-index, and this will make reference to the frequency in the Fourier space, right? So also important to the discussion that follows is that we consider the L2 space here with this very classical representation in Fourier analysis, where we have psi alpha, and so this is basically the Fourier coefficient, and here we have the complex exponential basis function, and we consider that these are R-squared integrable. So we also know the Hilbert space here with the semi-norm also bounded, and these are the two main structures that we will be using throughout this work. Here, J is the unit, the imaginary unit. The Fourier coefficients in a classical sense are defined as the projection here in equation 4. And the norm of this field here, before we show the semi-norm, here we have the norm of in equation 5 in this HK space. So this K, it may be a fractional derivative. So we may have a fractional gradients or fractional Laplacians, as you wish. With this construction, we can handle those type of functions. In a classical sense, we have the inner product defined as between psi and omega here as the product of these two, the inner product of these two vector functions, where the second argument I use, as opposed to most literature, I use, well, not most, but half of the literature uses the second argument as a complex value. And the other half uses the first argument as the complex in the inner product, okay? But here I'm using the second argument as the conjugate, sorry, okay? So in the first problem, what we will be doing is this minimization showed in equation 8, where the first term represents the misfit between our approximation and U, that is our data, pointwise data. Then we have the possibility to include immersed boundaries, which is included here in the second term, where we penalize then this vector field in the normal direction of this boundary. And then the third component, which is really important here, is a Tikhonov type of regularization using a fractional Sobolev semi-norm. Okay, so here K makes reference to the derivative we will be penalizing, and epsilon is this Lagrange multiplier, if you wish, or penalization parameter. So, and this will be subject to the divergence of V being equal to 0. The second problem is slightly different, but the same idea. We have the misfit here between V plus var sigma, where V will be divergence free and var sigma will be curve free, and we want basically to decompose U, given these measurements of U, into these two components. Okay, and then of course we have to penalize in a Tikhonov way the field V and the field var sigma, subject that the divergence of V is equal to 0 and the curve of var sigma is equals to the null vector. So these Tikhonov terms here, they are important because they guarantee that our approximation is regular enough, and by the Sobolev embedding theorem. So for 2 dimensions, we have to penalize the derivatives that are greater than 1, and for 3 dimensions, we have to penalize the derivatives that are greater than 1.5. So now I will tell you a little bit about how I construct this Fourier approximation. So here I have as I said before, when I have a function here with a bold-phase index, that makes reference to a Fourier coefficient. Okay, whenever I have this vector with an index that is a calligraph letter, that represents the approximation. Okay, so here we have VI, that means that is the approximation V constructed with the multi-indices contained in this I. And it will be basically the Fourier series, or the sum of these Fourier coefficients that are complex value coefficients times the complex exponential function, right? And in the Fourier setting, to compute the divergence is rather simple. And if we want to impose the divergence of the velocity equal to 0, we just take the inner product of the Fourier mode with the Fourier coefficient, and we constrain that such that this inner product is 0. Similarly, to have a curve-free field, we have to take the cross product between the Fourier mode, the alpha here, with the Fourier coefficient, and set that to 0. So with these two constraints, what we get basically are two fields that are in principle unrelated, where one is divergence free, the other is curve free. There are many implications that come from this constraint, and we can. These are all the implications. If you can see in equations 14, 15, and 16, all of those two constraints, they yield all these equations. But what matters here for us is this equation 16.2, which says that the Fourier coefficient V alpha inner product, the complex conjugate of the Fourier coefficient gamma alpha, they are equal to 0. And basically that tells us that the L2 inner product between this div free and this curve free is 0. So they are orthogonal by construction. So this is the important thing. We have two fields that are divergence free, curve free by construction, but they are also orthogonal by construction. And why this is important? Because having two fields that are orthogonal by construction allow us to say that our Helmholtz decomposition exists and is unique. So now we take again our optimization problem, but we write in terms of our finite approximation. Before we had an infinite dimensional problem. Now we are dealing just with a problem where we want to find the Fourier coefficients in this statistical learning sense. So the only difference here is that I plugged in the V, our approximation VI. And now I remove the constraint because I can search for these coefficients in this constraint space where the divergence is 0, and I call it HK div 0. And this is not as we usually have in the literature when we say that a space is divergence is H div, meaning that the divergence of the field is L2. Here we are, this is a bit stronger in the sense that it's more restrictive because the divergence of the field is equal to 0 always. Okay, but that's why we just added the 0 here to say H div 0 instead of H div. And yeah, probably I forgot to mention, but these are complex representations, and to impose that, I mean, since we are working with the physics of fluids, we want these fields to be real valued fields. So we have to say that the coefficients V alpha, they have to be equal to the complex conjugate of the coefficients V minus alpha. And similarly, for the case of the Helmholtz, the Hodge-Helmholtz decomposition, we just plug here in our optimization problem our finite approximations, and we end up with this optimization problem in 22, where we will be searching for VI in this space H div, and var sigma j will be in this space curve H curve. Okay, and they have similar representations. The only difference here is the condition divergence free, and here we have in 24 the curve free condition. Okay, so I will try to explain how I construct these approximations, because so far I think it's fair if we say that given a multi-index I, we can construct in a pretty simple way this approximation VI over sigma j, right? What is a bit more involved in terms of construction of this approximation is how to construct the index set or the multi-index. So to do that, we construct an approximation in a greedy manner. So first we have to define things like the energy, and the energy is just the inner product, the L2 inner product here of the field with itself, and the energy of the boundary. This is what I define as the epsilon of del A. So consider an index set A, and so assume that this index set is given in this picture. The whole set is composed by all these spots, red and black. The boundary are the black spots. The boundary are all the terms that surround this index set. So what we expect from Fourier analysis is that there is a decay that is quite fast, is exponentially fast of these modes as we go away from the index 0, 0, right? So we start with a very small index set, an index set that is 3 times 3, in 2 dimensions, for instance, meaning that we will take 9 basis functions to construct our Fourier approximation. Then we increase this set to 5 times 5, and we can evaluate the energy of the boundary of this index set, right? And if we see that the energy of this boundary is relatively large compared to the whole set, then we keep increasing this set in this greedy manner. Okay, the question is, how do we drop the basis function? So once we augment the index set, we evaluate the contribution of each basis function to the whole approximation. And we say, okay, I am going to drop 50% or 80% of the bases with less energy, or the Fourier modes with less energy. And then we increase the set again, solve the problem again, measure the energy of the boundary, take the less representative modes in terms of energy, drop them, and keep increasing this until I reach a boundary where the whole boundary has a contribution that is irrelevant to the approximation. Does that make sense? Sort of. So I will show you very simple examples for the divergence-free projection. For that, let's bear in mind that we will show the error of these approximations. So the error is just defined as the norm of the actual field minus our approximation, and the L2 norm is just the integral, the square root of the integral of the error square. Okay, and to compare our results, we will use radial basis functions, and we will use these multi-quadratic, inverse, Gauss, linear, cubic, and so on, basis functions. They depend on, many of them depend only on R, which is the radius, but some of them depend on S, and S is just a parameter that ideally we have to fit or to find the optimal one, to doing some hyper optimization, right? And here I will show you naively taking S equal to 1 and 2, these 10 cases for these basis functions, and we'll compare with our approximation. In this problem, we take we take a function that is a composition of sine and cosine. And we will be working in a domain that is 0 to pi squared. And I will explain in a very detailed way this first example, and all the rest I will just walk you through the results. Okay, but so here we define the residual boundary energy as 50%. That means that each time step I will increase the whole multi-index set, and I will keep only the 50% most energetic basis. The other 50% will drop, and we will keep doing that until the energy of the boundary represents 10 to the minus 7 or 10 to the minus 6% of the total energy of the approximation. Yeah? So in this case, we used an epsilon. The epsilon was the parameter penalizing the fractional Sobolev semi-norm. Is 10 to the minus 6 here. The derivative we penalize is the 1.5, and after 6 outer iterations, because we have to perform 6 optimization, we have to solve 6 optimization problems as our index grows. And sorry, so this set here is the final set of basis functions that we include in our approximation. The blue ones are the ones that we kept. Okay, so see, this problem is rather simple. That's why the set is a bit odd. And mainly here you have all the energy in the 3 times in the first 9 basis functions. The rest is not actually very energetic. But the red basis functions here are the basis functions that are not in our approximation. Okay, so on the left here we have the analytical underlying field, velocity field we use, and on the right we have our approximation. And here we are considering again only divergence-free field. We had access here to, I think, about 10 velocity measurements. And these, on the bottom plot, we have the error, and the dots are the velocity measurements. So differently from what people usually do in PINs, in physics-informed neural networks, is that we have fixed measurements because the problem we are interested in, we have access to fixed measurements that we cannot change the location of this, okay? And here we have the solution using radial basis functions. And as you see, there are many unphysical features that appear here if you compare with the original field. And you may complain and say that this comparison is unfair because I am imposing the divergence free. And by the way, sorry, I assume that you knew, but when I say divergence free, that means that we have mass balance. So this divergence free is linked to this conservation law of mass conservation for incompressible fluids. Okay, sorry for that, always. Anyway, so one may say the comparison is not fair enough because here we are just using an approximation that is completely unaware of the underlying physics, whereas our approach here, we are considering only divergence-free fields. And yeah, it is what it is. So this is the error of these approximations, and they are, of course, quite high. Here in the first table, we have the L infinity error, and the second table is the L2 error. So you can see that the L infinity error for our pistol approximation is 0.5, and all the rest, they are above 30 something. And the L2 error is our approximation is 0.03, and all the rest is greater than 1.
Sorry, could I have a question? How do you compute these errors?
I compute the difference because in these problems I know the underlying solution, the underlying field.
Okay.
I know what it should be. So then I compute the difference, and then I can compute the L infinity and the L2 errors.
Thank you.
But in general, we don't know, right? We don't know the underlying field. In this problem is just to show how we use immersed boundaries, and we consider that we have one velocity measurement at the end of the domain, and we have immersed boundary that is a circle. And yeah, we have all the parameters, but I think it's not worth discussing all of this. So basically, we have that arrow represents the velocity vector at that point. That is what we know, and we have this boundary. So the whole information comes from this velocity, and that the normal velocity to this boundary is 0. And this is the solution we get, again, considering that this is a divergence-free field. So then in 3 dimensions, we have the Taylor-Green vortex, and we aim at reconstructing this. This is the field, is also a combination of sinus and cosinus. And this is the index set we get in 3 dimensions. You can see that these sets, as the dimension increases, these sets start getting sparser and sparser. And in this problem, actually it's not that very sparse, but if we start increasing the accuracy of our approximation, we start getting a better, more sparse tensor. This is basically the reconstruction, and the error in this is pretty small. I think this problem had access to 30-something measurements. And we have on the left the magnitude of the velocity field. And in the middle, we have the Q criterion, is a criterion used in fluid mechanics to identify regions where turbulence may be more intense. And then we have on the left here, we have the velocity field sample at some random points. This is just a perspective of this reconstruction. And if you're familiar with the Taylor-Green vortex, you will identify the vortex here in the middle. Yeah, I had access to 64 velocity measurements, not 30. And now I'll show you the Kelvin-Helmholtz instability. This problem was done with actual data coming from a direct numerical simulation. Basically, we have 2 layers of fluid, one going to the left, the other going to the right. And the aim of this example was to determine the optimal penalization parameter. So we drew this L curve. The idea is to draw this plot where we have in the X horizontal axis, we have the misfit, and in the vertical axis, we have the penalization, in this case, the fractional Sobolev norm. And we start increasing this parameter epsilon, this to penalization parameter, and what we get is something that should look like an L, but since our approximation is constructed in a greedy sense, then we will have different approximations and different index sets. So this plot actually doesn't look like an L. But anyway, our goal here is to find a point that somehow is the closest point to the origin of this plot. That will be the ideal penalization parameter. That is a point that minimizes the L2 norm, or the fractional Sobolev norm, semi-norm, and the misfit at the same time, right? And these are the index sets we obtain for these different approximations. The different parameters of penalization. The optimal one ended up being 10 to the minus 3. This is, on the left is the direct numerical simulation, on the right is our reconstruction. And you see that the error is concentrated where we have a sharp change in the velocity, and that is somewhat expected, since sharp changes are, usually you need a lot of samples to represent sharp changes, and spectral bases don't like sharp changes either. So, and this is basically the problem we want to solve, which is basically take the wind and do the reconstruction of the wind field based on measurements done at weather stations. This is in the UK. This is the divergence-free reconstruction of these measurements for the day 5 of March. And in the middle, we have the wind speed, and on the right-hand side here, we have the vorticity. Why is it important to determine the underlying wind field? Well, of course, it's important for forecasting, but it's also important if we want to determine regions where one should place a wind farm, and also for the pollution propagation. And there are quite a few applications in terms of pollution propagation as well. But our goal here is to determine ultimately where are the optimal places to implant wind farms. Okay, now I try to go quickly now through the Helmholtz decomposition. Again, I will not describe the details of the simulation, but here we have to penalize the fractional Sobolev semi-norm of the divergence-free field and the curve-free field. So we may use different parameters for this penalization, and we may penalize different derivatives, although it's not clear whether we should penalize different derivatives. I don't think it makes a lot of sense, but doing the hyper optimization, we may find that we need to penalize different derivatives. So for this problem, I didn't write the underlying function, but we end up with these two different index sets for the divergence-free field and for the curve-free field. But the errors of these approximations in the L2 sense are here. So this is the first one is the error of the total reconstruction. The second is the divergence-free, and the third is the curve-free, and the L infinity error on the second column. In this problem, I think it's in this problem. Let me see. Yeah, in this problem, we also measured the speed at which this energy decays as our index set grows, and we got that we have an exponential convergence with that means this, right? With this b being about -20. And the orange is the curve-free, and the blue Yeah, and the blue is the divergence free. So here we have the iterations. The iterations means at each iteration we are growing our boundary. So I'm picking the largest index. Okay, so in this iteration, and here on the vertical axis we have the energy of this whole boundary. Okay, so if you assume that this is a sort of a circle, or and the circle is growing, and where inside the circle we have all the bases, I take the radius of these bases and I'm plotting here in the horizontal axis. Okay, and the energy of all the bases on the boundary is on the vertical axis. And these plots are basically the error heat map of this reconstruction. So as we refine, you see that these reddish spots, they start disappearing because our approximation is getting better. And here what we have is the underlying field. So in this first picture, figure A here, this is what we see in the simulation, okay? But we know that this field is the sum of this divergence-free field with this curve-free field, okay? And by having access to this underlying field, we are able to reconstruct the field, but also the divergence and the curve-free of these two fields. There are some discrepancies here in this lower boundary and upper boundary, but that's okay. Overall, these approximations are good. Here are the overall errors, and I'll try to speed up because I want to reach the stability. So here I'll show you a three-dimensional problem, and these are the final index sets I get for the divergence and for the curve-free, and they start becoming more sparse as we grew in dimension here. These are the errors of these reconstructions. Again, pretty small. We are pretty happy with these reconstructions. Here we have access to this figure A, to these velocities A, and we reconstructed the divergence free and the curve free pretty well. So the errors are concentrated on the boundaries, but this is because these functions are not actually periodic, and I didn't use any padding here. I could have used, but I didn't. And even though the results are good. So the application of this, why we are doing this, one of the applications is to find hurricane formations before they are formed. So we have access to satellite data, and there are some algorithms that can give you velocities from a sequence of images. And so we have access to those velocities, and then we can perform the Helmholtz decomposition. So this is a picture of the 1993 storm of the century, and basically this the satellite data was given to us as these vectors representing the velocity, and we aim at reconstructing this underlying field, and from the divergence-free field we can detect this hurricane eye formation. I say that this before it was formed, but supposedly you can see the vorticity here in the original field, but supposedly the hurricane eye was not formed yet. Okay, so you have to believe me, but we were able to find this vorticity, this vortex, sorry, that represents the hurricane eye formation. Okay, now we are going to the point of today. We have 5 minutes. The Stokes problem. So the Stokes problem is a problem where we have a system of two differential equations. The first equation is the momentum equation. Nu here in the first equation is the viscosity of the fluid. V is the velocity, P is the pressure, and F is a forcing term. And the second equation is the mass equation, as I said, the divergence of the velocity equals to 0. And so subject to periodic boundary conditions for the pair pressure velocity, and we assume that we have a given mean that will simplify the discussion when it comes to coercivity. For the weak formulation of this equation 32, we have this weak form here, where in the first we have the bilinear operator A, where the first argument here is the trial, the second is test, and we have the bilinear operator B related to the second term of the equation, related to the pressure, and the linear form L, which is related to the the forcing term. Okay, this saddle point problem it's quite tough to solve in general, because it's a saddle point, and the explicit form of these bilinear forms are given in this equation 35. And what we aim here is to find a discretization of pressure and velocity such that we can guarantee that the solution of this PDE exists and is unique. Okay, as we see in, okay, sorry, if we plug here our physical approximation using our Fourier constructions, we get these weak forms. I will not discuss them, but if you want, we can discuss afterwards. So I will instead discuss the existence and uniqueness of the solution of this problem. So if we can guarantee two things here. The first is that the operator A is coercive on the kernel of B. A is the bilinear form related to grad of grad trial, grad test. So if we can guarantee that this bilinear form is coercive on the kernel of B, where B was the pressure times the divergence of the test, yeah. And we can guarantee that the supremum of this B is bounded from below, then we can say that there exists a unique solution V and P belonging to these W and Q to the mixed variational problem. Okay, so, and usually the problem here is finding the pair P and V where this condition 2 is satisfied. Important to the discussion that follows is that this V here has norm 1. Okay, it can be written in different ways, but so if we take our approximation and we compute the form B, we end up with this expression where we have the sum over the intersection of the index set of the test for the pressure and the trial for the pressure and the test for the velocity. We end up with this form, with this term. So where we have here Q alpha, this is the test the test Fourier coefficients of the pressure, and here we have the trial Fourier of the velocity. So what we can do, we need to guarantee that this is actually bounded from below by this by this gamma q, norm of q. So what we do is then, okay, if we now have to play with the index set. If we say that the index set for the pressure is included in the index set of the velocity, we can always say that there is one guy. We pick a guy where alpha inner product, the Fourier coefficient, complex conjugate equals to this guy. Okay. And why we need k to be included in I? Well, because the norm of v needs to be 1. So we need to leave 1 degree of freedom free to make v normalized. The other degrees of freedom we can use to find this guy. So we found this guy here, this v alpha, such that if we plug in our bilinear form, we end up with this b bilinear form being equal to the norm of q. And that means that if we found one guy where this bilinear form is bounded from below, well, then of course it will be true for the supremum as well, right? And what we have is that if the index set k is included in I, then we will have a stable pair of pressure velocity, right? If we don't do that, we cannot expect a unique solution. Does that make sense? So the point here is to have an approximation or two approximations where this inequality holds. Otherwise, we cannot guarantee the existence and uniqueness. To show you that, I consider first this first problem where I take, I don't care about this, about this int-sup condition that says that the index of the index I of the velocity should be larger than the index K of the pressure. I just neglect that. And I have this optimization problem where I minimize the residual, but I also project the data onto these approximations V and P, right? So we have data in velocity and in pressure. And here we also add the penalization of the divergence of the velocity. So meaning that I'm not using the divergence-free construction, okay? So I'm just using classical stuff here, nothing fancy. And the same number of degrees of freedom for the pressure and velocity, meaning that K is equal to I. And then I postulate the problem in a different way, where I now use a space of divergence free. Why? Because if we use divergence free, the int-sup condition is just about the coercivity of A. So we need just to guarantee that A is coercive, and then we can guarantee the existence and uniqueness of our problem. So in this problem, what I do here, on the left, we have our first approach where we neglect the fact that the index K should be smaller than the set K should be smaller than the set I. And on the right-hand side, what we have here is the divergence-free construction. And if we use 3 times 3 basis functions in plot A, we don't see any problem whatsoever, right? Probably because we have very few basis functions. In the plot B here, we also see basically the same using the divergence-free construction. But as soon as we start increasing the number of basis functions of our approximation, things go south, and we lose there is no unique solution. On the other hand, we still have stability and convergence if we use the divergence-free construction. The same happens if we use more degrees of freedom for the velocity than for the pressure. And yeah, I wanted to take the chance to thank Raul for helping me with my habilitation. I just published with Springer, and thank you also for the invitation.
Thank you, Luis. Very nice talk. Do we have any questions? Hello, anything online? So I have a question. So you do this kind of inverse problem. So do you ever take into account, let's say, observational errors if you have, let's say, satellite data?
No, no.
Could you extend what you're doing to such a setting?
I don't know. I don't know.
Are you considering extending this in general to a more stochastic setting where you could have uncertainties, for instance, in different model components?
To be honest, the idea of dealing with the errors, I was planning to do something more in a more deterministic way because I didn't have a clear idea. So the idea was basically to remove the curve component because I was interested in, since we know that the wind should be divergence free, was to reconstruct the divergence component and get rid of, and the curve component would measure basically the error in a deterministic.
Okay.
But probably that's not the best alternative.
So what are do you thinking about extending this work in some additional kind of direction?
Yeah, now what I have to do is make it efficient in terms of computations, and then I have a huge data set, and I plan to start working with the forecasting part.
Okay. Okay, Alex.
Yeah, no question. Are you ready? Okay. So when I was approximating functions with tensors, sometimes it's helped to split function in two parts, and one which is very close to singularity and which is far away from singularity. And then I have very good approximation of both. But if I try to approximate function directly without the splitting, then tensor ranks are very high. So it's, do you observe something maybe here? So with if applied to you, you try to use pins to approximate your vector field, you fail. But if you split vector field into components and try to apply pins to every single component, maybe it will be better. Did you observe something like this or not?
No. No. And if you see the plots, the error of the three components are basically the same, at the same level. So I haven't seen anything like that. But I mean, there is no singularity here, right? Everything is very smooth.
So for example, it's a reason why we always subtract mean value from every snapshot, because then approximation is better. If we keep mean value inside of each solution or snapshot, then we observe higher tensor ranks. But okay, yeah. I don't know why, but I was thinking about this.
No, I haven't seen that problem. But maybe because the problems are very simple so far. Maybe.
I see that you're using some stochastic some optimization method to fit model.
Yeah.
So can you talk a bit about properties of this optimization problem if it's complex?
And the optimization problem,
Yeah,
if the optimization problem is convex,
if you know, if you investigate it.
well, the whole point of for the last problem, the int-sup, if you guarantee that the int-sup is, you want to remove you want to have a problem that is coercive. So it is convex for sure. That
Okay.
guarantees existence and uniqueness. You use if you don't respect this int-sup, then it's you may have many minima.
I don't know, because you had several works here, right? Like that,
Several
different.
yeah, the other.
No, I'm asking about both.
The
But
algorithm
yeah,
I am using.
but they're related, right? Because you had those Tikhonov regularization parameters added
that
to
helps a lot.
get more better regularity, right?
Yeah.
And then once you have some complex problem,
but
you are using.
I use BFGS because
BFGS.
the problems are not very big.
Okay, yeah, makes sense.
If the wind data gets really big, then you know better than I do. I mean, you have to go to stochastic
optimization. But I think one of the advantages here is that you can get a very good approximation even with small data points, like a small number of points in comparison to the.
It depends on the scale you're looking at.
Yeah.
If you want to go to really small scale, I don't.
Yeah.
Probably it's not. I mean, it depends. It depends on the scale you want. If you want to have the big picture, I think it's good enough.
Okay, good. Thank you very much.
Thank you.
Any more questions from the audience? Okay, so let's thank Luis again. So this concludes this session. Thank you.